This question is taken from the ENGAA 2020 section 1 paper. It is question 21. So we have a DC transmission line with two metal wires. Each wire is 8 kilometers long with cross-sectional area 1 centimeter squared. So we have these wires and then the current, so one going from right to left and the other coming from left to right. The resistivity is 2.5 times 10 to the minus 7 ohm meters. The potential difference input is 24,000 volts and the power supplied is 120 kilowatts. At what rate is energy being wasted as heat in the wires? So we want the energy dissipation rate. So this would be about the power dissipated. And how do we go about this power dissipation? Well, normally with power you can think of many equations, IV, V squared over R, I squared R. But for wires, especially in DC transmission lines, the common misconception is to use V squared over R, where you have V as a total potential, when what you're meant to do is use the current going through the wires and square it and then times by the total resistance. And this is because in a similar vein to internal resistance, these wires take a fraction of the power that we're putting in. So this resistance is associated with the wires, and so they'll take a certain potential, which is IR, not the whole potential 24,000, but a certain potential V dissipation times the current going through them. So the equation we should use is P dissipated is I squared R, where R is the resistance of the wires. So we can get I quite easily because the I in the circuit in this transmission system can be gotten from the total power input divided by the voltage input, which is 24,000. This is P in over V, so this is 5 amps. So this current times the voltage gives you your total power input. But then how do we get the resistance? Well, they've given us resistivity, so the obvious equation to use is resistivity times the length divided by the area, the cross-sectional area. But what length should we use? Well, this DC transmission line seems to have the current going in one way and then back. So this current must be going along one wire in order to transfer energy and then coming back along. So the total distance is 2 times the length, so 16 kilometers. So if we wrote this, we have the resistance is resistivity times the length times 2 divided by the cross-sectional area. And then if we try to work out the power dissipation, if we had an expression for it, we then have 5 squared times the resistivity times 2 times the length divided by the cross-sectional area, converting it into meter squared. So can we cancel out anything in order to make this a nicer expression to multiply? And we can cancel out 10 to the minus 7, 10 to the 3 divided by 10 to the minus 4. But then also 2.5 times 2 multiplies quite nicely to 5. So we have 5 squared, 5 and 8. And this is just 25 times 40, which is 1000 watts of power dissipation. So compared to the 120 kilowatts that we are providing, this is quite a low power dissipation, I think. And the main thing that would have tripped a lot of students up in this question is the 2 times L. So these DC transmission systems work where the current goes to transfer the power that we need, but also it has to come back in order to stop charge building up at the other end, our output, where we're providing electricity. So it has to be part of this loop. As you know, the current must go one way and then return back. And then the other misconception can be when to use I squared R or V squared over R in these cases. So the current is always the power input divided by the voltage. This is always true because that is the current times the voltage is the total power input. But then for the power dissipated, the total power, not all the power goes is dissipated in the wires, so only a certain fraction, because they'll take a certain amount of the voltage, essentially. So they'll take IR of it. So there'll be the other part in the circuit that we're trying to output it into, so we need I squared R as a power dissipation relation.